What I wanted to tell you about is really iterated monodromy groups, which is a topic that we already heard in Volodya's talk yesterday. And I wanted to focus very much on the particular situation of quadratic polynomials, with one positive side that many things become much simpler when you concentrate on this special case, and I will try to give many examples rather than two general theories. And the other is that we could push the theory in the direction which really interests people in dynamics, namely not the critically finite maps, but critically infinite. So how do you take care of a critically infinite map which corresponds to infinitely many punctures on the sphere, as we saw in Hamel's talk? It is much more subtle in terms of the parameter space. And also from the group theory perspective, where we have to deal with more complicated groups. So first, very quickly, the general setting. That you will recall from yesterday that we have a self-covering of a manifold M. Oh, sorry, self-covering of a topological space M, which you can assume is metric. And we can assume also the map F is expanding locally for the metric. But I won't write the hypothesis yet. If we take T in M, we produce the tree of preimages of T. And this is a tree varying continuously.
Recording in progress.
So this is really a disjoint union of all the preimages, and you must think about this as some sort of an abstract tree. So we have M here, and the covering. We have our base point T, and then there are two preimages, and then there are four preimages, and so on. So this is really the tree that you should keep in mind. Written in this way, it's a set of vertices, and I connect by F. So I connect Y to F of Y. Okay, so as I move my point T, as I said, these points will move too. And if the map is expanding, then these points will move more slowly than the way T moved. In all cases, if I drag T around the loop in this space, then these points will also be dragged, maybe along a loop, and maybe along a path which is not a loop. So this is the monodromy action. Which is that the fundamental group of my space based at T acts on this tree. Right? So for now, I'm just repeating what we saw before. But the important thing is that there is just one. So let's say that this has degree D. So this is going to be a D-regular rooted tree. There's just one D-regular rooted tree, a vertex, and then D ancestors, and D squared, double ancestors, and so on. But there are many ways of writing it, even though there's only one. We would like to identify this tree with something symbolic. The natural symbolic object to associate to it is the tree of words. Words over an alphabet with a these symbols. And here we connect, say, a word W, say W, so x1, xn, to x1, x-1. We connect two sequences by an edge if they agree up to position n-1, and then there's an extra letter for one of them. And one way of doing this identification is to give some labels. Maybe I should start using colors. So call this one 0, call this one 1, for example. And then by lifting them, I could say that these will be zeros, these will be 1. But a very nice way of doing it topologically, let me use a different color for this, is that we can copy the preimages of T in here. So this will be a image. And I can choose some paths in here and label these paths 0 and 1. This gives me another way of identifying the vertices of this tree and the edges, and to do some symbolic identification. So the point is that this path here is the same as this 0. And I can take the lift of this little squiggle here that is based at here. There would be a little squiggle here and a little squiggle here. And from here, there will be a little squiggle here and a little squiggle here. And now this I can use to give some symbolic encoding to the edge here, lifts it, and to the edge here and here. And this is not the same thing as the encoding that you see by following these arrows. But it's a very good way of doing an encoding. And in fact, this is the one that we will use.
I call it geometric coding tree, unless your original was dynamical tree.
Yes. So using this, we can describe the monodromy action. This is also a picture that Volodya explained. We'll take X to be these paths. And now there is a map from X cross G into G cross X. And I will write this map in the form xi hash G equals H hash xj. And this hash symbol means just concatenation of appropriate lifts of paths. So here I say I take xi, which will be maybe this path here. And then I have an element G, which is maybe this one in the fundamental group. I want to write the concatenation of this xi with G. Well, that's not possible, because xi stops here and G starts here. But there's a unique lift by F of G that starts here. And, well, it's in fact going to be this thing here. You have to always remember that the picture takes place in some other image. It will be this arc here. And now this is a path from T to a preimage of t. And there's a unique way of writing it as some loop at t followed by a path from t to that premix. So the choice of j here is dictated by where this lift of g stops. It has to be this one. And then there's a unique element h that gives this equality as an equality of paths up to homotopy. So this is the data that we have just from looking at paths and seeing how they are lifted. And this data is sufficient to reconstruct the action on the tree of words over X. Let's go back. So X upper styles the space of words. Now, unfortunately, there's a terrible confusion in this area, which comes from left and right choices. There's just no way to get out of it. I wrote this map in the natural order because this is how you see concatenations. I could have written these paths in a reverse direction, then you would have seen everything in the other order. I think the only important thing is to stick to the same convention between the first and the last page of an article. And apart from that, there's just no way out. One of the reasons is, in fact, that you shouldn't think about left and right, but you should write things on a square. So there would be an up-down in another direction. Maybe I will explain this. In all cases, if you're given G in the group, and x1 up to xn x star, well, now I'm going to act from this side onwards, just because I don't want to introduce any extra artificial reversion. Maybe I should write my words in this way. Well, you just write x1 up to xn dot g, and then this map phi tells you that when you have a g, you can switch it past the x and get a new element of x and a new element of g. So this will be some g1, y1, and then there's an x2 here. So we'll switch these two, and then this will be give here g2, y2, and so on. And I can rewrite it using my rule phi in a unique way as y1, yn, and then there will be some extra element h. So this is the result of the action. Okay, so there are many convenient ways of doing these calculations, and I certainly don't want to harass you with all the different formalisms. But it's probably a good idea, nevertheless, to know that they exist. So, maybe I should give an example. Maybe the example even fits here. So Volodya gave the example of the basilica. I want to do something simpler to start. Z squared, seen as a covering on C minus 0. So in that situation, the fundamental group G has, oh, T is already used. Let's say gamma, generated by a loop. Around 0. And there's the puncture. I must choose a base point somewhere. So let's choose it here, for example, t. Then t will have two preimages, the square root of t somewhere here, and minus the square root of 2. And now a choice of a basis will be an x0 here, and maybe an x1 here. Okay, so to compute phi, I must say x0 and gamma, and x1 and gamma. What are they? Well, if I do x0 and then gamma, so gamma is in fact rather, it's a loop-based t, it will rather be something like this. So one lift, and again I should use colors so not to clutter my picture. One lift will be like this, and the other lift will be like that. Now if I do x0 and gamma, this is really up to homotopy the same thing as x1. And if I do x1 and then gamma, this is the same thing as x0. Okay, so this is the algebraic description of the map Z squared. In that, well, that's one. That's what you wanted? Yes. You have a map to G cross X, and so. Oh, no, it's not. Thank you very much. Yes. So if I do x1 followed by gamma, I stop at x0, but it really is gamma followed by x0. Yes, thank you very much. Yes, it's not just the endpoint, but this x1 followed here is really going once around. Right, so this is one way of writing the information. And in some sense, the best way of writing the map phi is by a square. That if you put an x0 say here in the gamma here, then you'll put an x1. We do the I put a gamma and x0. I'll have an x1 and a 1. And for gamma, x1, we'll get x0 and gamma. So all these things come with a And in this way, if you want to compute the action of gamma on some word, well, you write gamma here, and you write the word here. It will be x0, x1, 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 x0, 0, x1. And then there's a unique way of completing this picture with the squares. And here I have to use this square. So I have to put an x0 and a gamma here. And then I have to put, again, the same square. Again, the same square. Now I have to put that square, which gives me an x1 and a 1. And then the 1, I didn't write the formula for 1, because obviously it's enough to write it for generators. 1 will just give me, again, a 1. And this is the result of the action on that word. So if you do things this way, you never have to worry about left and right. Unique natural way of working. Another convenient language is to say that you want to focus really on the action of the elements. So rather than writing a map from x cross g to g cross x, you write a map from the maps from x into g cross x. So alternately, we can say that gamma gives, well, now I have to write the pair of elements that I get here. This is coded x0, this is x1. And I have to remember what happens to the symbols themselves. So we'll say that x0 and x1 are exchanged. And the note. This is exactly the same data, just written with different symbols. And finally, one more notation for this is if you are so lucky that there exists S finite for which phi of x cross S is contained in S cross X, then you can write a graph. With vertices S and edges, they will go from some S to some T with label X goes to Y. And this you do each time phi of XS is equal to T. And these are called automata. So in this situation, the automaton would have one vertex, they're called states, labeled gamma, one for the identity, then 0 becomes a 1, and 1 Now, reading paths in these automaton is the same thing as reading words. And quite clearly, if I follow the path with x1, 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 x0, 0, 1, that will be, sorry, I got all of this. x1, 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 x0, x0, x1. By looking at the input symbols on every edge, I look at the corresponding output symbols on the same edges, and this gives me exactly the result of the action. So I can't really say that one notation is better than the other. Still about this example here, I want to do just a little bit more, which is that we're allowed to mark other points than just 0. I could also have decided to mark 1 if I wanted. And I could also have added one generator, which does a loop around 1, delta. This is perfectly legal, even though it doesn't seem very smart. And then the recursion for delta will be that if I do x0 and then the lift of delta, well, one lift of delta will be delta itself. This will be that. On the other hand, if I do first x1 and then the lift, this lift surrounds nothing. So it's invisible, and it just gives me again x1. Good, so one question I have not answered is, why is this in any way useful? So one reason I believe it's useful is that you can use it for calculations that involve some extra homotopical data. So for example, I talked here about the map F, and I described the recursion for the map F we could also have considered the map f of z equals 1 minus z. That doesn't seem to be a very exciting map from the dynamical perspective. This is a degree 1 map, so the basis x used to describe it will have a single element. Let's call it y0. And if I go back to my picture here, I have a loop around 0, loop around 1, and they will just be exchanged. So the recursions that I have will be that y0 hash delta is gamma hash y0, and y0 hash gamma is delta hash y0. Now I can compose. So if I look at the composition of 1 minus z with z squared, this is essentially the basilica. After change of sign, this is the basilica. And you can compose the operations. The basis will naturally be, well, I first do x and then y, or I first do x1 and then y. And if you go through this, you will recover the recursions that Volodya gave us yesterday. So there's an important message behind this, which is that you can construct more complicated objects, such as the basilica, by starting by something you understand well, like z squared. And here, you can put, in fact, any Möbius transformation. So this lets you describe all quadratic polynomials as soon as you understand z squared, and you understand the recursion associated to a Möbius transformation, a degree 1 map. In fact, you can do all rational maps in this manner. So you don't have to do this complicated path tracing all the time. You have to do it just for the map z squared, which we could do without too much difficulty, and then use compositions. Now, it's quite natural to describe Möbius transformation or mapping classes in terms of group theory. Here, this map 1 minus z is just exchanging functors, so its action on the fundamental group is just the switch, the generator. And we want to combine this efficient notation for mapping classes with the dynamics coming from Z. And this is the way to do it. Okay, so yes, well, how do you describe a mapping class? Say of a punctured sphere. A finitely punctured sphere. Well, in general, what is a mapping class? So a good way of representing one is saying that it's an automorphism of the fundamental group. And if it's an automorphism of the fundamental group, this gives me directly the recursion here, which says that y0, my single basis element, hash g, is phi of g, the image under the automorphism, hash y0. This is just a way of copying the automorphism of the free group. Aha. That's an excellent question. I don't want to go too far into this, but the whole point about having this flexibility of choosing a y0 is dealing with base points. So once the y0 has been fixed, I've made a choice of a base point. And if I look at this object up to a choice of y0, then this is base point independent. But this is really the whole beauty of the theory. Okay, so
In the mapping class group is group outer.
yes, exactly. And the inner automorphisms precisely correspond to a change of base point. A change of base point. and replacing the y0, so this basis element, which maybe you thought should be just a constant path at the base point, into some loop expressing this change of placement. I'll say something that is probably very useful in this respect when I get to more details on quadratic polynomials. There is maybe yet just one thing I wanted to add about the automata picture that maybe I can do it on the oh yes, good. So we can be so lucky that there is a finite S, and then we draw a finite graph. In general, we could have done this for any S, even the whole group itself, if we wanted. Now, when we are in this favorable situation of the existence of finite set S, containing, say, the group's generators, we do have a complete encoding of the data by this finite. Now, I didn't explain this maybe sufficiently, but if you want to act by gamma squared, well, you will just put two gammas next to each other, and you will complete this picture. And here we have to use just once this tile here, which gives us an x1, and then all of these will be ones. So it copies x0. What we see in particular, that acting by gamma squared lifts to an action by gamma each time, and then by the identity. So in the automaton picture, gamma squared could have been added, but it directly leads to gamma. And gamma cube and so on would also lead to here. There is another element, gamma inverse, which does the opposite as that one. Now we are here in this very favorable situation that there exists a finite attractor in this automaton. In that wherever you start from, any element G, it will follow arrows, and eventually it will hit this set. This is exactly what Volodya had defined as the nucleus. And then there are very strong results that say, for example, that if the map F, the self-covering we started with, is expanding, then there will exist a finite nucleus. And this nucleus, well, the automaton that you see here, not just the set, but the graph structure that I grew, is really the invariant characterizing the map. Okay, so this finite if f expanding. Good. So now I want to really move to the situation of quadratic polynomials and see as much as possible about them. We can raise. I don't think I can move two things at the same time, right? No, I cannot. So my goal is to give you something like a iterated monodromy group dictionary. In that, the study of quadratic polynomials has been pushed so far in the last 50 years, since the birth or so of Hamel, that there are many concepts that have proven useful, and many of them have a translation to the algebraic world of these iterated monodromy groups. And I will not give many new results, but I will hopefully show that concepts on both sides are tightly related, with the hope that if we want to study cubic polynomials, higher degree polynomials, rational maps, or other such objects, they would help in leading to useful generalizations. So the example I will mostly concentrate on is the rabbit. Probably the nicest one, on which we can describe things. So this is the map whose Julia set will look like this. The post-critical set consists of these points. And I can consider the map F as a map on the Julia set, or just on the sphere punctured at these 3 points. Remembering that it's not exactly a covering, because, well, there are the pre-images here, which don't know where to map to. But I still have this unique path lifting property on the sphere punctured at these 3 points. So there will be a natural group generated by 3 elements going around these punctures. Now, how do we write the recursion, or the automaton, or the squares, or any of these pieces of data? So one thing we can do, and this takes directly inspiration from what complex dynamists have always done, is we cut here at angle 1/14, and that's 1/14 plus 1/2, which well, okay, I could take 1/7. Yes, sir. So I can cut in this way, and I can use this as a basis for my bisect. I will put my base point t close to infinity, and then there will be some preimages of t. Well, one preimage would be close to infinity also. Let's not bother about where, and the other preimage will be minus that one. I can take one connection, let's say x0, which is this one, and another connection, which is this one. Same point at the other one. So this will be x1. And now, I would like the nicest possible formulas to, in particular, this situation of an automaton. Well, for this, the solution also is already well known. I have to find what is called an invariant spider. So these are the legs of the spider. The body of the spider is here at infinity. The spider has legs going to these. So saying it's an invariant spider means that it's a collection of curves, such that if I lift them by the map F, either they become trivial or they're part of my collection of curves. And in particular, there is an algorithm due to Dirk, where is it? Oh, hello Dirk, and Hamal, that says that you can construct, you can reconstruct maps out of topological data by a spider algorithm, which says you start by any spider, and you lift, and you lift, and you lift, and you straighten the legs, and you will converge to an invariant spider. An algorithm that actually works in practice in quite a few cases. It can be very much improved using iterated monodromy groups, precisely because we can decouple the lifting operation, which is analytic, and the group theory information. It's like in a mapping class group. We don't have to construct complicated edges as segments. We can construct them as words in a group. In all cases, if we have an invariant spider, such as this one, we can write a recursion. Here the recursion will be, let me write it in this form with the arrows. And here exchange x0 and x1. So this is also something that you can write as a graph. A goes to C, goes to B, goes to A, with the labels 1, 0, 0. And here, 0. So this is the beginning of the dictionary, probably, which is basis, cut along critical value, critical point rate. And then what I would call automaton. So existence of an automaton would correspond in my dictionary to the existence of an invariant spider. And we can do a little bit more. In that, there's a sequence here, 1, 0, 0. But this 1, it's both a 1 and a 0, in fact. If I had written the inverses of the elements, I would have switched these. So what you see here is something like star 0, 0. And in fact, this is the general situation. So maybe I can call this a theorem, which is that for periodic critical point, the recursion has generators A1 to AN, and the formula is that A1 is 1 AN, and then this exchange, 0, 1, and AI plus 1 is 1 AI or AI 1. And this is in some case where sequence U1 is 1. I remember this position. This is UI is 0. So this defines a group K of U. And U is the sequence U1 up to U n minus 1 is the needing sequence. So and then this is label on cycle. Yeah. Now, I do want to check the time. This is maybe not the best choice of a basis for the bisect, a choice of connection. And in fact, there's another choice that I want to move to now. So again, the rabbit, again the base point t here, and I can think that a polynomial is a deformation of the monomial z to the d, z squared in our case. And we want to give a special status to this. So we could want the connections between t and its preimages to be close to infinity. So I could choose this path. This is x0 and this is x1. Now this will have the advantage that if I consider this generator here, g infinity, the formula for g infinity is exactly the one that we computed in the beginning for the map x squared. So g infinity will have this form, or in automata language, change. So this will be 1, 0, 0 goes to 1, 1. Now, having infinity on the picture is not very convenient. So let me draw the same infinity, but the way we think about it on the plane rather than on the sphere. So this will be my now, and in fact, the t would be rather here, and the preimages, which would be square roots, would be rather here. This is x0. This is x. Now remember that we had the tree of preimages, which was a completely abstract tree constructed from the map F. But it also has an actual representation here. I can compute the lifts 0 of this. And this tree will approach the Julia set. And if you remember that the map is expanding, this means that these lifts get shorter and shorter, and they will approach and they will collide. So in fact, the place where they collide will exactly correspond to some group elements that constantly have some activity. So I'm going to connect this to the nucleus. But in all cases, by making this choice, this finite choice of an x0 here and an x1 there, I can again write the bisect. Now my natural generators would be external rays. Well, external ray, then maybe an internal ray, continuing through it. So I can write, let me give them names. So this is 1/7, this is 2/7, and this is 4/7. So G4/7 is easy to write, because one lift will be 2/7, I'm taking a square root, and the other lift will be inexistent. 2/7 is also easy to lift. And finally, the 1/7 is not so easy to lift. Well, it becomes 1 over 14, bigger head than before, and then it crosses here and then returns that way. So on the first side, in fact, it's encircling these two in reverse order. That would be G1 over 7 inverse, G2 over 7 inverse. In the second coordinate, it's doing these two and then also the 4 over 7. G4 over 7, G4 over 7, 4 over 7. And here again, exchange x0. So this looks a little bit messy. And the reason it's messy is that we maybe didn't choose exactly the right generators. A much more clever choice of generators is by considering the Hubbard tree, or more precisely, the extended Hubbard tree, with some mark in here. So if I want to have a state-closed formula, a finite set S, with labels to itself, well, I should consider this element as part of my set S, and I should take this one, and then I should write the formulas for these and keep working with them. And in fact, S can be conveniently written as those paths crossing once. If you take something that crosses once, well, its lift will cross it most once. So it's automatically a set having this property that it gives you finite. And in fact, you can draw the automaton directly on the picture by putting your states here for crossing here, 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 and here. These are the 8 states of the automaton. And I won't do it now for lack of time. But if you choose these states, and you take this to represent the path that crosses once across the Hubbard tree, from connecting to infinity by the extension, there's a unique way of coming back, then you will have an automaton. So I want to keep here, basis will be connect at infinity. So we're thinking about the deformation of the quad. And then automaton, well, the existence of an automaton is really the existence of a Hubbard tree. And then the recursions themselves, what you see here, are the itineraries. So yeah, it seems magical to write formulas and lift them and so on, but if you know the Hubbard tree, you just draw the automaton next to it, and you have it. Okay, so now let me try. 3 minutes. Well. Sorry? Oh, so you mean less than 3 minutes?
Another 1 minute more.
Sorry?
4 minutes.
4 minutes more. Yes, very good. So one thing I want to say is that so if the post-critical set is infinite, so possibly then sort of this same picture will hold. If you look at these formulas, you can multiply 4 over 7 times 2 over 7 times 1 over 7. And this is really multiplying them coordinate by coordinate. You see it cancels here and here. You get again the same element, 4 over 7, 2 over 7, 1 over 7. So this product here is the same thing as G infinity, the loop that we had. So the general situation is the following, that we have G infinity expressed as a product of elements Gi. And this could be infinite product. To take an infinite product, you need some topology. So in topology of, for example, the automorphism group of the tree on which you act. And then you have formulas of the form Gi is Gi minus 1, 1, or 1 Gi minus 1, except for the first one, G0, which will be equal to some product Gi on some index G0, and here, product of Gi's on some other set. And there's in fact a straightforward way of constructing such expressions. So I here, this I is countable, is ordered. And we can assume that it's a subset of the circle. That's the way its order is given. But in fact, here's the fundamental example. If you fix an angle phi, then you can construct generators G theta for theta in the circle. There will be, of course, continuously many, but all will be trivial except countably many of them. So G theta is G theta over 2, G theta plus 1 over 2. That's its recursion. And this is if theta not equal to phi. And G phi will be equal to here, the product on all theta in the interval phi over 2, phi plus 1 over 2 of G theta inverse times the product for all theta now in the closed interval. And here the exchange x0. Now these are the invariants that are associated to the angle phi. More precisely, the group we should consider is G sub phi, which is the group generated by all intervals. That's the product. J, any interval. So this lets me just the second I need for a theorem. Now I have to insert somebody here, which will be which is that the collection of G phi up to isomorphism, well, up to as subgroups acting on the tree, as subgroups of automorphism group of the tree is the same thing as the Mandelbrot set over combinatorial equivalence. So here I identify 2 points in the Mandelbrot set if they have the same hyperbolic components between z squared and themselves. So if same between them So Mandelbrot set here up to combinatorial equivalence corresponds here to a family of groups. Acting on the binary. And there's a natural relation on the Mandelbrot set, which is being a limb of one and the other. And there's a natural relation on groups, which I will not explain because Dirk forbid me to explain it. And then this is an isomorphism of posets. Thank you very much.
Thank you very much. In fact, there is no time for question, but one very short question I would allow. No questions from online participants. So again, thank you. And